morning, everyone. My name is Christophe Guyeux, and I come from the University of Bourgogne-Franche-Comté in France, and I will present my work related to the prediction of pre-hospital emergency transport in France. So, at the beginning of this story is the evolution of the interventions for the fire department of Doubs in France. As you can see, between 2006 and 2017, the average number of interventions per hour has been multiplied by a factor of 2, and we have some peaks of almost 100 interventions in 1 hour, and so for the firemen, they must find a way to make optimizations based to predictions indeed. So the objective of this work is to anticipate. Our goal is to predict the number, the type, and the location of the interventions for various reasons, for anticipate the number of interventions, and so increase the crews if needed for vacation scheduling, or in a larger scale to predict the future needs in terms of human and material resources. So we can, when we speak about firemen, so we think about fires indeed, and a fire is not predictable, but in France and as in various countries, the major part of the activity of fire brigades is personnel rescue, not fire. And when we speak about personnel rescue, we speak about accidents that are directly related to human activity. You have, for instance, more accidents during the days and at night, and during lunch you have a reduced number of accidents, and so on. And this human activity, indeed, it depends on various features, various exogenous variables like the weather, the holidays, the season, and so on. I give you here 2 examples. Ice falls occur in winter, not in summer, while drowning in output swimming pools in summer, not in winter. We have access to meteorology features via Météo France weather forecasting API. We have various stations close to the location of interest, namely the Basel station, Dijon and Nancy ones. We have all the features you can see on the screen for at each 3 hours since 13 years, and with missing data that have to be completed. The objective is to make predictions for each 3 hours, of course, but for each hour too. So we have added other features to this weather one, features of interest when we speak about intervention prediction of accidents. For instance, calendar features like the time of day, the day of week, day in the year, the month, and the year. And we have added information about holidays, either school holidays or public holidays, and ephemeris data like the time of dawn, of dusk, or the moonrise or moonset time, even the phase of the moon. Road traffic have been obtained thanks to Bison Futé website, in which we have color according to the traffic, indeed, for each day. And other features have been downloaded too, like water aids for a set of 22 rivers in the department, or epidemiological data thanks to the Santi-Web vigilance website. Our first predictions was based on gradient boosting for each 3 hours, for each block of 3 hours. We have obtained a mean squared error of 3.83 and mean absolute error of 2.98, which is really better when we compare with the baseline. And we are able to extract knowledge like the feature importance for each kind of intervention. Here you have the list of features for the suicide interventions. Of course, hour is important. People does not commit suicide at 3 a.m. You have an importance of the year due to we have particular years with epidemiology and so on that impacts suicide trends. But at the first, our first most important feature is June 21, which is summer solstice. So we can wonder whether such a feature is important to predict suicide. When we check it in a graph that computes the number of suicide interventions per day in the year, we can see that we have an obvious peak at the 21st of June. We have a multiplication of 2 of the number of interventions of this kind. Indeed, it's not a new result. We have a lot of publications in the literature that try to explain such a fact. As you can see in the abstract, annual patterns in suicide rates peaking near the summer solstice are well documented. So this fact was not known by firemen of the department, and this is an example of knowledge that artificial intelligence can bring to firemen. So we have improved the first scores I have presented earlier by using various approaches, and our model selection shows that the best results was obtained by extreme gradient boosting and the LSTM recurrent neural network. In this last situation, in almost 30% of the cases, we were able to recover exactly the good number of interventions. And if we accept an error of 1 intervention, we have more than 72% of accuracy. Another interesting thing is that with extreme gradient boosting, we are able to recover some peaks related to flooding events, for instance, which is not the case with long short-term memory, as we can see on the graph, which indicates that a mix of the two methods may be the best solution. The main limitation of this current approach is that to predict the number of interventions in the next hour has no real interest if we speak about operational events. The number of interventions predicted in 1 hour, you cannot make any optimization to face a peak that is predicted in a so short delay. So even if we have good results for the prediction horizon of 1 hour, the main interest is to try to predict in 2, 3, 4, or 5 hours, or even the next day, or next month, or next year, but not. Okay, so the first idea may be to have the features in the future, and then to make prediction in the future. To do so, some features are known, like the months, the year, or even the holidays. Other features can be computable in the future, like Easter, Ramadan, time of dawn or of dusk, and all the features related to the moon. But some features cannot be computed in the future, like the weather data, the flu incidence, the rates, the road traffic, and so on. We have tested various approaches. The first, the most basic one is to have just a time series forecasting approach, which means that we don't use any feature. Second approach is to still operate a regression based on features, but only on the features that can be known or computed in the future. We remove all the other ones. A third approach is to use the current features to predict the interventions in 1, 2, 3, and 4 blocks, and so on, until the error becomes too big. So the current result may impact the interventions in 3 hours, for instance, if we have a lot of rain. The approach number 4 was to duplicate the values we have 1 year before for the features that cannot be computed. Or for some features, we can access to predictions. So an idea may be to predict the features in the future, and then to make the predictions of the interventions. For instance, we have access online to weather forecast. So either we download predictions of features, or even in the sixth approach, we can predict by ourselves the evolution of features and then the evolution of interventions. Maybe the solution is a mix of 2 or more approaches depending on the prediction reason. So as we can see, the signal has a high autocorrelation rate. If we compare the number of interventions between now and 1 hour in the past, we have a correlation of 0.56. If we compare the correlation between today and 1 day before in the same hour, we still have some correlations. Even between 1 Monday and the next Monday, we have obviously some correlations. And if we consider Christmas holidays between 2 years, you have a very strong correlation. So this seasonality of the time series is strong, and this autocorrelation may be useful. But as we can see, this correlation decreases when we go further in the feature, we have a fading over time. If we have a good correlation between two successive days, this correlation reduces bit by bit when we increase the horizon. The first approach may be the persistence model, in which to predict the prediction is what occurred in the past. Indeed, you just duplicate the last known values. As you can see, the two signals here are shifted. By doing so, we have a good root mean squared error, which is better than the baseline, but which is worse than the average per hour. And indeed, we cannot predict the peaks, for instance, and we have always a delay. An autoregression model has been tried with a lag of 67, which was automatically chosen thanks to a statistical test. By doing so, we have computed the root mean squared error and mean absolute errors, and this time series approach performs well when we are within a few days, but of course its performance reduces dramatically when we increase the horizon. In this slide, we have removed the features that cannot be computed exactly, and I only plot the mean absolute error here. So in average, this score is good, even if we have some peaks at in the worst case 2 interventions. We are still much better than the average per hour, because we can take into account the seasonality in the year, like the months in the year, or even the trend between 2 years. But if we consider small prediction horizons, so the performance is worse than the time series forecasting. In this approach, we try to predict by using current features. We can to predict the interventions in 1, 2, 3, and so on. And by doing so, we have a good performance. And the root mean squared error is indeed improved a little when compared to the previous approaches. But we have some seasonality in the errors that reduces the interest of this approach. You have 2 curves here between the best previous approach and the current one. As we can see, peaks in root mean square error are reduced, while in the mean absolute error we have smooth curve indeed, which is in average better than the previous approach. But we still have bigger errors due to epidemic peaks or flooding events. So an important remark is that the feature importance is evolving depending on the prediction of horizon. If you think about the current number of interventions, it indicates a local trend. It is very useful when you focus on the horizon of 1 or 2 hours to know if we have a lot of interventions now. But this knowledge becomes less and less important when you try to predict in 1, 2, or 3 days. In any situation, the time in the day and the year remain very important, like other calendar features. But if we speak about weather features, their importance, of course, decreases when you enlarge the prediction of horizon. Knowing that it's currently raining is not useful if you want to predict in 3 days. It's the same thing can be used for diseases. The incidence first increases and then decreases. The water level of rivers do not evolve very fast, so it still remains important when your prediction of horizon is of 3, 4, 5 hours. But you may have a change in the rivers of interest. And if we speak about public holidays, of course, they are no longer important for an horizon of prediction which is larger than 2 days, for instance. In the last approach, we try to use the last year features, but as you can see, the mean absolute error and the root mean square error are far from our best models. So this approach is not good at all. Indeed, during training, the model understood the importance of current weather, predict future interventions, but the current weather of this day may be totally different from the weather of the same day 1 year before. And for instance, we can announce that it is snowing when the weather is fine. So it's time for the conclusion and perspective. In our test, we show that short-term predictions are best performed by using the time series forecasting approach. When we consider mid-term predictions, the best way is to use state-of-the-art regression models like extreme random boosting or long short-term memory with the current features. And for the target, you consider a given hour in the future. For long-term predictions, we still to perform new investigations. The best approach is to reduce the details. I'm not sure that predicting for each block of 1 hour in 1 month is very useful. Perhaps the solution is to try to predict for a given day if the horizon of prediction is of 1 month. Okay, so this is the end of my presentation. I thank you for your attention. If you have questions.
Okay. So thank you, Dr. Christophe, for the presentation. Actually, I have one question before I proceed to the attendees' questions. If you can go back, please, to the slide that talks about the data set. I think it's in the beginning. Probably the previous one that contains text. Okay, this one, yes, that's correct. You mentioned that you have missing data inside the data set. Did you try to solve this problem to find the missing values, or how did you treat these missing values?
Yes, we performed a linear completion. It was solution was the easiest one indeed.
Okay. Anybody else would like to ask about this presentation? Yeah, please.